Okay, hello everybody. Welcome to our section. And I am Yang Jin Kim from Sungmyeong Women's University in South Korea. And the title of this section is the Advanced Statistical Method for Complex Data Challenges. So we have wonderful three presenters. And before starting, I'm so happy to participate as your chair in this section. And I would like to appreciate Dr. Dong-Yoon Kim to suggest this section. And also thank you, Professor Park, to organize this section. And finally, thank you, Professor Min Jae-ri and Yang Yeon-jo to accept our invitation. And we have three speakers today. Since our section holds for 1 hour, we have plenty time to focus on these three interesting topics. So let me start. Let me introduce the first presenter, Professor Min Jae-ri's talk. Her topic is about disentangle unobserved heterogeneity and the statistical approaches to characterizing longitudinal trajectory of medical uses among various at-risk patients. Please welcome Professor Min Jae-ri.
Thank you so much. Can you all see my slide?
Yes.
Thank you. Hello, everyone. It's great. First of all, many thanks to Dr. Kim and Park for organizing and chairing this session. It's my great pleasure to talk about tonight, statistical approaches to handling measurement issues and data collected from heterogeneous population. With an advanced biotechnology, the study of biological processes for treatment of disease has been rapidly developed. A better understanding of whether medications are effective in medical diagnosis, prevention, and treatment of disease plays a key role in an increasing number of biomedical studies. Especially for the chronic disease, these studies sometimes involve investigating the short or long-term use of medication usage over time. It's been really interesting to explore how the level of medication usage changing over time and how it differs among those patients. And it's complicated, like a dynamic or complex associations with disease progression over time. However, most commonly used measurement tools for medication usage rely on participant report. So these participant report sometimes collected over time could be missing or skipped for various reasons. This missing pattern may also dramatically differ between individuals, and it does complicate determining the trajectory of medication usage and its true effects for the patients. In the era of precision medicine, of course, researchers are increasingly sensitive to the heterogeneity among those at-risk individuals. Due to these types of gaps and biases in participant reporting, statistical modeling to assess these measurements especially challenging. So inappropriate handling of these complex issues can lead to definitely misleading findings, especially when it depends on multiple sources of variation over time. So we found these issues in our motivating study example, SOAS, the prospective study of outcomes in ankylosing spondylitis, AS. This is multi-center core study of AS patients who are enrolled from 5 different sites and followed up to at most 13 years. One of the study goals was to find out the factors that are associated with disease progression and severity over time. Specifically, our focus was on evaluating longitudinal effect of one of the medications called non-steroidal anti-inflammatory drug, NSAIDs. So NSAIDs are commonly used to treat ankylosing spondylitis patients because it helps patients managing their chronic pains and inflammation. So we wanted to assess how the level of NSAID use changes over time and its association with radiographic severity or damages, which are measured by the score called MSES, Modified Stroke Ankylosing Spondylitis Spine Score. So we consider analysis cohort of 536 patients who met a certain criteria and had at least 2 years of follow-up data, radiographic data available. So medication usage data were collected at every 6 months. So we define NSAID data, index data, based on level of doses and number of times that particular medication use for each patient. However, we face challenges in analyzing these index data. Why? We found almost 70% patients had missing NSAID data at least one visit. Only 12% people had missing NSAID data at just one visit. And about 50% patients had missing data for up to 6 visits or more. This could be due to the missed or skip visits for follow time, but most of cases, these missing values were due to the limited ability of self-reporting. So that leads to inaccurate and untenable information. So basically, patients usually take multiple medicine together, and they do not recall all the details, how many they took and how often they took, what type of meds, and they sometimes forgot and misunderstood the questions itself. So it definitely complicates determining the trajectory of medication usage and its full benefits for AS patients. So there could be an attempt to fill in some pieces of missing information for those who never used or had persistently high or low doses of NSAID, but not easy to do for those patients who switched their level of NSAID uses frequently over time, which we found from the majority of the patients in our study. So we thought it might be helpful to explore the longitudinal pattern of medication usage and their heterogeneous trends first before we jump into the handling missing or incomplete data. That's our main idea. As you know, compared to naive or other methods for handling missing data, it's been shown that model-based imputation methods such as multiple imputation, other methods provide more valid statistical inferences. However, many of those are likelihood-based approach that produces some specific estimations or assumptions related and assume sometimes normality of the data such and such, which may not be valid for certain scenarios. In our study, NSAID index data were never normally distributed and V-shaped and range between 0 and 100, and transformation never worked. Moreover, the unobserved heterogeneity among those individuals I described earlier was a crucial issue. So we wanted to seek some other options, of course. Quantile regression methods has been used in longitudinal analysis as an important alternative to mean-based regression model because it's robust and flexible to non-nullity or heteroscedasticity, and its implementation for the imputation has been widely used. Specifically for handling missing data, Bayesian methods have been also widely used because of its unknown additional quantities for which a posterior distribution can be estimated. Bayesian approach can be also applied to the quantile regression model using certain distribution. We can also call this Bayesian quantile regression, BQR. The imputation using gift sampling methodology through the MC-MC integration can be also used for quantile regression, and it requires a certain generation of Markov chain from posterior density. As I mentioned earlier, we wanted to first identify the longitudinal trajectory of medication usage over time using appropriate methods such as group-based trajectory modeling, such and such. There are multiple different methods available, but many of these are likelihood-based methods, and sometimes it's not good for heterogeneous population, rarely used for imputation. So our idea was to identify the cluster of the individuals following similar patterns of data over time and incorporate those findings into the imputation processes. while accounting for complex correlation or covariance structures of repeated measured data over time. So in this study, which was recently published in Journal of Biopharmaceutical Statistics, we propose latent class-based statistical approach under mixed effect of Bayesian quantile regression framework that incorporates unobserved heterogeneity for handling medication usage data, such that we can provide better understanding of data association, especially in the situations where we are interested in different patterns of data over time that may lead to different types of risks of disease outcomes. So basically, let me just start with a simple basic quantile regression model first. Let Z star be measurement for ith subject and time j. Suppose we define the linear regression model here, where xij is factor of covariates that can include the time of measurements. And beta is an unknown parameters vector of regression coefficients. If tau conditional quantile of error term given xij is assumed to be 0, a quantile regression model has the form here, where beta tau is a vector of quantile specific regression parameters. Then we can derive the objective function here to determine the parameter estimators, where the loss function here is reflecting the weighted residual, the contribution of residuals. Transition of Bayesian quantile approaches to quantile regression can be addressed by modeling the error distribution using a symmetric Laplace distribution, ALD. We can define random variable Z here if it is following ALD with probability density function here, where tau is skewness and mu is location, and I think the location and another the parameter mu is location parameter and sigma is scale parameter. And assuming mu can be determined as a linear combination of a set of covariates, and Z is following ALD, likelihood for an independent observation can be expressed like this. Given this, we can define distributions of Z here. For the longitudinal data setting, linear mixed effect model can be expressed as a linear function of a set of variables x and v for fixed and random components respectively, where parameter beta tau is for fixed effect and gamma I for random effects. To mimic the distributions of NSAID index in our study, we assume that the variable z has a logit normal distribution. A linear mixed effect model for logit z can be defined here. This leads to probable density function determined here. Then we can define conditional distributions of logit z here. When the patient belongs to the class K, this model can be extended for allowing us to for the latent classes model by introducing a latent categorical variable Ci that takes a value between 1 and k. Then we can define distribution of Z with k here. Given that, model with latent class can be extended and expressed here to the fixed effect and random effect coefficients. And gamma for random effects specific to class K has multivariate normal distribution. For latent class modeling, we define class indicator Ci, which has categorical distribution, taking the value k with probability pi. We can also determine the probability pi through a generalized logit model with r-dimensional covariate vector W, like this. And ck is an integer variable ranging from 1 to k, and we assume that number of classes k is known. So we need to use a particular model selection strategy, such as EIC, for determining the optimal value of k. For imputation through gift sampling under Bayesian framework, we have to derive the posterior distribution of the parameter by using this prior distribution of parameters. Based on these priors, specifically we need to simulate Z star, largest Z star, from Bayesian predictive distribution here. Our goal is to impute the missing values by taking independent draws from the distributions we determine here. So we carry this out in this deep sampling the algorithms, where we define imputation step, where we update the imputed values, and posterior step, we update the parameter estimates. All the details of sampling steps are shown here. I'm not going to go into the details. For the Gibbs sampling, we generated 700 iterations for each data set. We took the imputed values from the five iterations to form 5 imputed data set. All details regarding the conditional distributions of parameter are presented in this following several slides, but I have to skip these slides for because in the interest of time. Apologies. So after we generate imputed data set, we conducted longitudinal regression analysis, like typical analysis, to evaluate the association between imputed variables and dependent variable. To obtain the parameter estimator of interest, we just simply combine all estimator as a mean, multiple estimates. For the variation, for the variance parameter, we use bootstrapping, resampling methods to get the standard deviation of estimates. We conducted a simulation study to check how robust are proposed methods across different scenarios that include different error distributions. For example, here, normal distribution, symmetric distribution, which we used exponential distribution, and heteroscedastic model with variance that depends on the covariates, such and such. So basically 300 simulations data sets with sample size of 500 or 200 were generated. We also consider class membership model and different specification, distributions and parameters. All the details I'm gonna skip because all are very complex. So this is table presenting the results of a simulation study for 30% missing specifically based on scenario. I just talk about different error distributions here. We fitted our methods without latent class incorporated, BQR1, and with incorporate latent class incorporated model, BQR2. And other methods also applied includes MCMC-based method. And we also conduct complete case analysis, which is using complete data, observed data, not complete data, observed data only, observed. So we calculated the relative efficiency, RE, for comparing each estimator with the omniscient estimator Omni as a gold standard that is based on complete data without any missing. MSE and relative efficiency are presented for each parameter, alpha 0, 1, 2. Overall, our proposed methods provide more efficient estimators, which means reflected by high relative efficiency than other methods that were used for comparison. And also demonstrates that our methods is not sensitive to the traces of distribution as compared to MCMC-based method, for example, that assume normality of data and such assumptions involved. Similar findings were observed in the presence of 50% of missing data. We were able to also conduct the simulations for a small sample size, such as 200. We observed very similar performance of our proposed method. Finally, the fun part. We finally applied our method to the SOS and SAID data I introduced earlier. Basically, we wanted to assess the longitudinal association between NSAID index usage and radiographic severity data over time in the presence of missing NSAID index data. And we were interested in how their trajectory changing over time. So our methods actually considered after including disease duration, gender, race, and clinical relevant characteristics after consulting with clinicians. These are trace autocorrelation function plots, ACF, for each parameter of interest, which indicating good performance of repeated iteration. So these are are showing how the data are imputed. So across four different latent classes we identified by the proposed method. You can see very different trajectory over time and distributions, distinguishing the observed data green area from imputed data gray area by the proposed method. As you can see, more zeros were imputed in group 1 compared to other 3 groups, while higher values were imputed in group 4 and 3. This table shows adjusted ratio and p-values for complete case analysis observed, and those from imputed NSAID index data by 2 other methods, MCMC Bayes method and our proposed method. After controlling for other variables, there are noticeable differences across these 3 different methods, corresponding p-values and estimates for the NSAID usage that are categorized into 3 groups: not use, low and high use. The results from our proposed method indicated that higher NSAID index inversely associated with radiographic damage compared to those no use group, and that was statistically significant. But other 2 methods did not result in that significant associations we found in our proposed method. This is really important figures. Last slide. This figure shows the estimated longitudinal trajectory from our proposed method, which identifies 4 different latent classes for progressor group and non-progressor groups. As you can see, there are really different patterns of trajectory found across the different groups. Patient in group 1 had minimal or no use over time persistently, while patient in group 4 were on high use persistently over time. Actually, also, we found that patient in group 4 were on high use actually progressor group decreased slightly over time, while it was not observed in non-progressor group. And group 3, NSAID use was increasing faster during the first 6 years among the progressor left-hand side, but this was not observed for the non-progressor groups. In group 2, progressors NSAID intakes decreased much slower compared to non-progressors. It was faster. So these findings would have been missed using traditional longitudinal analysis and imputation. And also, it definitely matches what clinicians expected. So we use these methods for other related studies and published. In summary, we propose new statistical method that can not only account for missing data over time, but also that can deal with longitudinal trajectory over time. The proposed method can be used to characterize different heterogeneity characteristics in longitudinal trajectory of treatment effects or other type of progression, and properly account for that in imputation processes. That's it. Thank you so much for your attention, and thank you again for the opportunity for presenting this study. Thank you.
Thank you. Thank you, Professor Lee. The application of Bayesian quantile to missing longitudinal data is so interesting. And thank you again. And now, since we are on the schedule, we move to the second speaker, Dr. Yang Hyun-cho. Welcome, Dr. Cho.
Okay. Good night, everyone. First of all, I would like to thank Dr. Kim and Dr. Park for the invitation. I'm Yang Hyun. I'm working as a postdoc at Columbia University. And today, I'm going to talk about how to predict optimal predictors of general small area parameters under an informative sample design using parametric sample distribution model. So let's start with an introduction. Before diving into the main topic, I'm gonna explain the 2 preliminary knowledges for this study. First one is about what is the small area. So a small area refers to any subpopulation where a direct estimator has inadequate precision due to a small area specific sample size. So here is an example of an agricultural survey from Ohio. So in the state level, the total sample size is more than 3,000. However, when you focused on a specific county, the sample size of each county varies from 1 to 30 or even 0 for the non-sampled counties. So the core idea in small area estimation problems is to use model-based estimator to borrow information across areas, and I'm going to explain our model in the following section. And the second one is about an informative sample design. So a sampling design is said to be informative if the selection probabilities is dependent on the model outcome variable, even after conditioning on the model coverage. So for example, let's suppose that we are interested in estimating the prevalence of the diabetes in the population. And for the assume that we obtained our sample by selecting individuals from a health clinic serving for low income and uninsured individuals. These individuals are at higher risk for the diabetes. So if we make inference using this sample, then there may be an overestimation problem. So the key idea under informative sample design is that we need to, the population and sample complement distribution naturally arise, and we need to reflect these differences to avoid the biased inference. So here's the motivation of our research. First, Kapelman and Schwarzkopf 2007 showed how to predict small area mean of both sampled and non-sampled areas under an informative sample design. However, their method is limited to the linear parameter. Molina and Lau 2010 defined the procedure of obtaining the empirical best predictor of nonlinear parameters under the nested error regression model. However, their method is also limited to a non-informative sample design, and they do not consider the non-sampled areas. So we proposed a method that can address the prediction problems of general small area parameters for both sampled and non-sampled areas under an informative sample design. So now let's talk about our optimal predictor. First, let's assume that our finite population is generated under the following two-level model. So here, the subscript I and j refers to the area, and the j's unit in area I, and the ui represents the area random effect. And then we further assume that our observed samples are obtained through the following two stages informative sample design. So let's denote II and IIJ as the sample inclusion indicators for area I and the unit J for area I. So in the first stage, we select D areas with probability pi I, and in the second stage, we select small ni units within the selected area I with probability pi ij. As you can see, the selection probabilities are related to area random effect or outcome variables. So we are considering the two-stage informative sampling design. And then now let's talk about the best predictor. So let's define the small area population parameter set I is the function of the full population of area I. So here the function H is known. So under the scared error loss, the best predictor of the population parameter can be defined as the conditional expectation of the small area parameter set I given the collection of data ds. So ds contains the sampled unit and the sampling rate, which is the inverse of the selection probabilities. However, due to the complexity of function h, we may not obtain the closed form expression for the best predictor. So we can use the MC approximation for the best predictor. To make our life easier, let's rearrange the full population vector for the sampled area I with the collection of the sampled units YSI and the non-sampled units YCI, respectively. So for a sampled area, the expectation in the best predictor is with respect to the sample complement unit given the observed data. So by simulating the sample complement unit from the following conditional distribution, we can approximate the best predictor for a sampled area. And for the similar manner, we can define the best predictor MC approximation of the best predictor for the non-sampled area. So once we can derive the following two required distributions, then everything is done. To derive these required distributions, we use the relationship among distributions under an informative design proposed by Pepperman and Schwarzkopf 2007. So first, let's define the sample distribution for the area random effect and the sampled unit. I won't go through the details, but the point is that sample complement distributions and the population distribution can be represented using the sample distribution of area random effect sampled units and the first moment of the selection weight. So once we can specify the model for the observed data, then we can recover the sample complement and population distribution. So by using this relationship, we can derive the required distribution for the MC approximation of the best predictor. So for a sampled area, we need to derive the following sample complement distribution. So by conditioning on the area random effect UI, we can obtain the first hierarchical representation in the equation, in the first equation. And then because the sample, non-sampled units are independent with the observed data conditioning on area random effect, so we can get the second equation. And by using the relationship between these sample complement distributions and the sample distribution, we can get the third equation. And then lastly, for the similar manner, we can also derive the required distribution for the non-sampled area. So there are many ways to approximate the expectation, but we're choosing the sampling importance with sampling algorithm. So for a sampled area, we simulate the area random effect from this conditional distribution. And then we need to simulate the sample complement units from this unknown distribution. So to handle this problem, we use the SIR algorithm. So basically, we simulate the large K non-sampled units from the known density, and then choose one of them by using the importance weight. So we can calculate the Rth iterations population small area parameter theta hat IR, and by repeating from step 1 to 4 for large R times, we can approximate the best predictor as the mean of the theta hat IR. But in practice, actually, we don't know the model, a true model parameter for the area random effect and the sampling unit, sampled unit. So by replacing this unknown model parameter with its estimate, we can finally define the empirical best predictor for the sampled area. And for the similar manner, we can also define the prediction procedure for the non-sampled areas. So, so far, I explained how to predict general small area parameters and the definition of the empirical best predictor. In this section, I'm going to explain how to assess the prediction error for the proposed predictor. So let's talk about the MSE estimation. The MSE of the proposed predictor can be decomposed as the three components. The first component, M1I, is called the leading term, and this is the MSE of the best predictor. And the second term, M2I, accounts for the variability induced by replacing the unknown model parameter, true model parameter psi with its estimate psi head. And the third term, M3I, accounts for the variability due to the MC approximation of the empirical best predictor. So for a sufficiently large R, the third term is usually ignorable. So by estimating the first two terms and then adding them, we can define the MSC estimator for the proposed predictor. So to be specific, let's focus on how to estimate the leading term. By using the double expectation formula, we can define the unbiased estimator for the leading term in equation 6. Again, in practice, we don't know the true model parameter psi. So by replacing this unknown parameter with its estimate, we can approximate this unbiased estimator. And luckily, the theta hat IR, which is simulated during our prediction algorithm, can be viewed as the random sample from the conditional distribution of theta I, given the data under the estimated model parameter psi hat. So by calculating the sample variance of theta hat IR, we can define the leading term estimator like in equation 8. And furthermore, we show that under the two conditions, we also show that our leading term estimator is consistent. And then now let's talk about how to estimate the second term. The key idea is that we are trying to mimic the replacement of a true model parameter psi with psi hat using the bootstrap procedure. However, because we do not specify the full distribution for the sampling weight, so we only specify the first moment for the sampling weight. So we cannot implement a fully parametric bootstrap procedure. Instead, we use the asymptotic normality of GEE estimator using the jackknife variance estimator. So by simulating the bootstrap version of the model parameter estimate from the asymptotic normal distribution, we can finally estimate the second term. And then by adding the estimator of the leading term and the second term, we can define the MSC estimator for the proposed predictor. Here I use the subscript no BC because we also propose the bias corrected MSC estimators. So first, the problem with the current MSC estimator is that the leading term actually is not the unbiased estimator. But luckily, we can calculate the bootstrap version of the leading term estimator while we implement the, let's see, while implementing the bootstrap procedure for estimating the second term. So by using this, the bootstrap version of the leading term estimator, we can correct the leading term estimator. So by subtracting the estimated bias, we can define the additive bias corrected MSC estimator, or by multiplying this multiplicative factor, we can define the multiplicative bias corrected leading term estimator. Because the additive bias correction can produce the negative value, and the multiplicative bias correction sometimes is unstable. So we also propose the compromised bias correction using this cutoff. And furthermore, we also consider the general class of bias correction proposed by Her and Mighty. So by using this bias corrected leading term estimator, we can finally define the bias corrected MSC estimators as shown here. So now let's talk about the simulation study. So for every iteration, we simulate our population from the following nested error linear regression model. And then we generate our sample using the following two-stage sampling design. So we stratify the 150 areas into 3 strata and select 30 areas from each stratum with probability pi I, and then select ni units for the selected area I with probability pi ij. So as you can see, the selection probabilities are related to area random effect ui or the outcome variables, so which means that two-stage informative sample design. And we also consider the 6 small area parameters of interest. So for the linear parameter, we consider the small area mean. And for the nonlinear parameter, we consider the 5 these parameters. So for example, the exponentiated area mean and 2 quantiles, poverty gap indicator, and Gini coefficient. And here is the simulation result for the performance of proposed predictor. Okay, I see. Yeah. So PS is the predictor proposed by Pepperman and Statistical 2007. And then as you can see, this predictor is calculated based on the closed formula. So, it has a smaller bias and more efficient than our proposed predictor, but it cannot cover the nonlinear parameter. And MR is the Molina and Lau 2010 paper. They cover the nonlinear parameters, but they do not consider an informative design. So they show the biased result. And also they cannot cover the non-sampled area. And then here's the simulation result for the proposed MSC estimator with respect to the relative bias. And most of them are within 5%, but it is hard to say that which one is the uniformly best because the performance depends on the predictor parameters nonlinearity. So now let's talk about the application to the CHIP data. So basically, the CHIP data is a nationwide survey of the cropland to examine the environmental effect of conventional effort on cropland. Basically, a CHIP survey is a subset of a larger survey called NRI, and the soil loss on cropland is an important variable of interest in both surveys, but 2 surveys use the different measurement for the soil loss. So our goal is to construct the estimate of functions of LaSutu using USLE as a covariate. And then by transforming the LaSutu and USLE, we fit the nested error regression model, and we consider the 4 count level parameters with the original scale. And then here is the predicted values for the corresponding for county level parameters. And we were able to see that there is a more soil loss in the south, the counties in the south and eastern part. And also the coefficient of variation of each county is on average 20%. So I skipped many details because of the time limitation, but please refer to my current publication. And this is my co-authors, and thank you for listening.
Dr. Job, thank you for your presentation. I hope you had a great time in Yale. So we see you soon. And okay, I'm Professor Park. I'm so sorry to say this. You have only 15 minutes. So yeah, I'm sorry, and we don't have much time. So please welcome Professor Park.
Thank you, Professor Kim, for the kind introduction, and it's a great honor to be here, and I sincerely thank you all for joining this session. Today, I'm going to talk about the application of empirical Bayesian strategy in high-dimensional data analysis. And during this time, I introduce some cases where empirical Bayes methods are applied, and in particular, I will briefly cover a classification rule for high-dimensional data, which I published this year with one of my students. And as you know, I'm the last presenter in this session, so I'll try to be expeditious. So the presentation will proceed as follows, and let's start by looking at a motivating examples. This figure shows protein domain data from patients with neurodevelopmental disorders. And here, X and Y axis represent protein domain position and the number of mutations, respectively. So here we can model the number of mutations at each positions using a Poisson distribution. And usually the primary focus is estimating the unknown parameter theta, which influences the number of mutations. We can also see another example involving stratified sampling, and this figure represents some stratification of individuals based on some specific conditions like gender, race, age, something like that. Hopefully, the histogram of the interested variable for each stratum show different patterns. So in healthcare, it is common to assume that the variable of interest follows a normal distribution with unknown parameter theta. And also here, the goal is to estimate these unknown parameters, which reflect the characteristic of each stratum. For parameter estimation in Poisson distributed data, the optimal Bayes rule can be derived within a hierarchical Bayesian framework where we assume that the unknown parameter theta distributed from G. And here the function PG represents the convolution of the observed data distribution and prior function. So in here, approximating the optimal Bayes rule can be achieved by precisely estimating this function PG. Similarly, for normally distributed data, the optimal Bayes rule also have this form like this. So again, the challenge is to approximate this Bayes rule by estimating this function FG. Regarding the parameter estimation, there are two key approaches in the empirical Bayesian framework called G and F modeling. First, G modeling focuses on estimating the prior distribution, while F modeling concerned with the convolution function itself. So from the previous example, the main distinction between G and F modeling lies in whether we estimate these unknown prior G and then plug the estimated this G hat into the convolution function to derive FG function like this. Meanwhile, F modeling solely estimates this FG function without any consideration about G. In this talk, I will focus more on G modeling. In particular, G modeling is widely used in various fields. So, for example, in multiple testing problems, we can use the estimated distribution G to derive p-values. And meanwhile, in parameter estimation, G modeling also can be used to approximate these Bayes rules. If we investigate the G modeling in more detail, then it can be divided into parametric and non-parametric approaches, depending on whether distributional assumptions on the prior distribution are made or not. Specifically, non-parametric G modeling has the advantage of capturing a variety of structure of the distribution G. And so many studies have taken advantage of these strengths. So in line with this, starting from the next slide, I will introduce our proposed classification rule based on non-parametric G modeling. This study was carried out with my student, Seung-yeon Oh, who is currently working at the National Institutes for Mathematical Sciences in Korea, South Korea. First, let's assume we have n data points as follows, and here y represents group label. And vector x follows normal distribution with heterodestic mean and variance based on the value of y here. In that case, if we define xj and vj like this, then we can see that these variables follow some specific distribution respectively. And in here, we consider a hierarchical Bayesian model where the distribution of mu and sigma squares denoted as G0 and F0. Also, in here, these distributions are not unknown to us. For the previous model, several classification methods based on the G modeling have been proposed. First, the Sure method in 2020, published in 2020, assumes parametric distribution for both G0 and F0. And later in 2022, a study named MPML method relaxed the assumption of G0, relaxed the assumption of Sure method by treating these distribution G0 non-parametrically. However, both methods share a common feature, that is, they assume a specific distribution for F0. So the limitation of making assumption about the variance distribution becomes evident in the following example. This figure shows the histogram of sample variances from breast cancer patients and the marginal distribution obtained from Sure or MPML method represented by light blue and dark blue line. Here we can see that both methods fail to capture the bimodality present in the original histogram data. So this demonstrates that assuming a specific distribution for the variances could lead to a failure in proper capturing the data structure. So therefore, in this study, based on the G modeling, we proposed a fully non-parametric empirical Bayesian classifier where we estimate the distribution of both mu and sigma squares non-parametrically. So since our method adaptively reflects the distribution structures of both mean and variances, so we have named it mean and variance adaptive method, in short, MVA. So from the model setting, equation 3 to 6, we have seen before, the Bayes rule for mu and sigma squares can be expressed like this form. And here the function fxv is the joint density function of x and v given parameters, and fv is the density function of v given sigma squares. So here, estimating these two distributions f0 and g0 allows us to approximate these Bayes rules for mu and sigma squares. So the estimation of the prior distribution can be done sequentially. First, we can estimate the distribution of f0 by maximizing this marginal likelihood of v, and then we estimate this g0 based on the estimated f0 we derived before staging here. And actually, in non-parametric G modeling, an infinite number of distributions must be considered as candidates to find the unknown distribution. Yes, but since this procedure is impractical, so common approach is to approximate the optimal estimated distribution using a finite mixture form. Also, this approach has strong theoretical foundations and can be easily computed using some convex optimization algorithm. So once we estimate the prior distributions, then we can approximate the Bayes rules for mu and sigma squares using the estimated prior distributions. For simplicity, the optimal classifier under the independent rule is well known to be defined like this equation 13. And by plugging our estimates of mu and sigma squares in the optimal classifier, then we can construct our proposed classifier in here 14 equation. Finally, to validate our proposed method, we considered well-known classification studies such as FAIR, NSC, PLD, or Bootstrap, random forest-based, or SVM, something like that. In each case, we evaluate the accuracy based on misclassification rates, focusing on the skewness, distribution of variance, and some structures of mean distributions. That is, we considered a feature vector dimension in 10,000 with 25 training samples per group. And for each method, we performed 500 times to calculate error rates. Due to the time constraints, I will skip the detailed simulation settings, but the primary goal of the simulation was consider left skewed, right skewed, and symmetric type distribution of sigma squares. And we adjusted the degree of left skewedness as shown in these blue lines. And in the same way, we choose at different levels of right skewedness as indicated by these red lines. And for mu vector, we considered two settings, sparse and non-sparse setting. So in our simulation studies, we examined 6 different scenarios combining left skewed, right skewed, symmetric distribution for variances with both sparse and non-sparse distribution for means. So here, the following figure shows the misclassification rates of each method for left skewedness distribution of sigma square with mu vector with sparse structures. And each panel represents a different degree of left skewedness for F0, and these x-axis in all panels corresponding to a parameter that affects the difficulty of classification. So, and here, these red triangulars represent our proposed method, which consistently shows lower misclassification error rates. Similarly, when we distribution of the mu vector is changed to be sparse to non-sparse case while keeping the same distribution for sigma squares, then overall, our method continues to demonstrate lower error rates. In the scenario where sigma squares is right skewed, our method does not achieve the best result. In here, something like that. But this is because the Schur and MPML method shown in blue and brown lines are based on the assumption that sigma squares is right skewed. That is, in this scenario, is favorable for them due to their correct distribution assumption. But despite this, our method still performs quite comparably. And the strong comparability of our MBA method persists in the simulation as well. Even for symmetric distribution of variances, our method show promising results. And the effectiveness of our method comes from its nature to adaptively capture not only the structure of mu but also the structure of sigma squares. So by comparing these marginal distribution of variances estimated by all methods, we can see how well our method describes the observed data. So among the various scenarios we previous examined, we further investigate a few representative cases, and this all figure shows histograms of the observed V along with our marginal function estimated by our MBA method in red line. So this red line represents the marginal function estimated by our method, and overall we can see this red line closely reflects the observed data. We also checked the scenario with non-IID case, but all the case we can see our method shows promising results. And finally, we confirmed the effectiveness of our method in numerous microarray data sets. And especially by comparing the sample variance histogram with the estimated density functions from breast cancer data, we confirmed that our non-parametric approach better capture the data structure, that is bimodality. Yes. In conclusion, empirical Bayesian G-modeling offers a flexible and data-driven approach to estimating parameter in high-dimensional data. And based on G-modeling empirical Bayesian framework, our proposed method shows improved performance in classification problem. That's all I have. Thank you for your attention.
Okay, thank you. And thank you for participating, three wonderful presenters, Professor Lee and Dr. Cho and Professor Park. And I hope we'll be soon in the next section. So thank you for participating again.
Thank you.
Thank you. Bye.
Thank you.